In this video, we'll follow up and talk about the domains of a composite function. So let me remind you of how we defined the domain of a composite when we first defined the composition of f with g. We said that the domain of f composed with g is the set of all x in the domain of g such that g of x is in the domain of f. So hopefully this picture will help clarify things a little bit. If I take an x and plug it into the function g. To do the composition, I need to take that output and I need to be able to plug it in to the function f. So it needs to fall in the domain of f. So let's say this set is the domain of f. It doesn't need to be the same as the range of g. It won't always be, in fact. Now, there might be a value, let's call it t, that when I plug it in, I end up in the range of g, but not in the domain of f. Then I can't plug into the domain of f. There might also be values in the domain of f that we could plug into f and get something, but they're not in the range of g, and so we'd never have to plug them into f anyway. So there might be a small subset of the domain of g that goes into this part that's in the domain of f and the range of g. And this is going to be the domain of f composed with g. This t doesn't work. We can't figure out f of g of this t because we can't plug g of t into the function f. It's not in the range of f. So that's why things can get a little bit complicated. So let's do two examples. So, I didn't give you, okay, so I want to find f of g of x, and f of x is x squared minus 9, and g of x is 9 minus x squared. I want the domain of this. So if I'm first going to be plugging into the function g, I need to know the domain of g. G has a square root. We know that we can't take the square root of something negative. So whatever I subtract off has to be smaller than 9. So since 9 minus x squared has to be greater than or equal to 0, this says that x squared has to be greater than or equal to 9, which means that x has to be in the set between -3 and 3. So that's the domain of g, which means that the domain of f composed with g cannot be any bigger than this because I can't plug in anything else into g besides these things. So the domain of f is all real numbers. So I don't have any restrictions here. Whatever my output is for g is already going to be in the domain of f. So our picture looks more like this. So I might have a very small domain of g. I plug that in. It's going to give me a set inside the domain of f, which is all real numbers. So anything I get as an output, I'll be allowed to plug in to the f function. So that means the domain of f composed with g of x is -3 to 3. I'm restricted by what I'm allowed to plug into g. But just for fun, let's actually compute f of g of x. If I compute this, I'm doing f of the square root of 9 minus x squared, because this part is g of x. And so that gets plugged in for the x. So I get 9 minus x squared, square rooted, squared, because I'm plugging it into f, minus 9. When I square a square root, it undoes the square root. So I'm left with 9 minus x squared minus 9, which is minus x squared. It seems like the domain should be all real numbers for this function. But it's not because we have to plug into g first. So always compute it this way. Figure out the domain of the inside function. Okay? One more example. All right, so now I want to find the domain of both f composed with g and g composed with f. So again, let's first do f composed with g of x just to see what it is and for the practice. So it's going to be the square root of x squared plus 4. That's going to be the square root of x squared plus 4. This looks like it should have domain all real numbers because whenever I square something, it will be positive, so x squared plus 4 will always be a positive number. But we need to check it formally. We need to see what the domain of g is. Well, g is just the squaring function. I can plug in anything I want, so that's all real numbers. So anything I get for an output of g, I should be able to plug into f. But the domain of f is restricted, so x has to be greater than or equal to 4. Oh, greater than or equal to negative 4, because I need x plus 4 to be greater than or equal to 0. So if I plug something in, so I'm doing first g and then f, but the only things I'm allowed to plug into f are x is bigger than or equal to negative 4. If I plug any g in, anything into the g function, is it going to be greater than or equal to negative 4? Of course it is, because g is positive. So the range of g is all positive reals. So we'll always be able to plug an output of g into f. So putting all of this together means that the domain of g, of f composed with g, is all real numbers because we're not restricted by the inner function and we're not restricted by what can be plugged into the inner function, so it's in the domain of the outer function. Going the other way, we can still use this information. The domain of g composed with f, well, if f is my inside function, I am restricted by this. So this is all x greater than or equal to negative 4. Great. So hopefully this gave you some good examples for computing the domains of composite functions.